Okay, so the last type of chemical reaction that we need to talk about is an oxidation-reduction reaction. We call oxidation-reduction reactions redox reactions for short. And in a redox reaction, there is electron transfer between some chemical species that's acting as an electron donor and another chemical species that's acting as an electron acceptor. And so oftentimes the goal for redox reactions is identifying which reactant is the electron donor and which reactant is the electron acceptor. A lot of really common everyday chemical reactions are redox reactions. For example, corrosion of metals. In this example, calcium, solid calcium metal, is being put into acid, is being reacted with H+, right? So with some protons, and as a result, it becomes a calcium ion and hydrogen gas. So in this reaction, calcium is acting as an electron donor because calcium is giving 2 electrons essentially to H+. And you can tell because you can look at the starting material, and you can look at the ending material, the products, and you can see that calcium initially was neutrally charged, and now it's a 2+ ion. So it's lost 2 electrons. It's donated 2 electrons to H+. And we'll talk about this a little bit more in the future slides, but I just want to give you a sense of what you're going to be trying to identify with these kind of reactions. And like I said, they're really common types of reactions. So this one is the corrosion of calcium, but iron rusting is another redox type of reaction. Also, anytime you're combusting something, there's transfer of electrons. And even in the demonstration we did in class with the hydrogen gas and oxygen gas to form water, that was an example of a redox reaction. And another really common one, as glucose is metabolized into, energy, glucose undergoes a series of redox type of reactions. So the main thing is being able to identify or assign oxidation numbers to different chemical species in a reaction, and that'll allow you to determine what is the electron donor and what's the electron acceptor. I'm going to tell you the rules next for assigning oxidation numbers. Okay, so when you're assigning oxidation numbers, the first rule is that each atom in an element has an oxidation number of 0. So for example, zinc metal, 0. Molecular oxygen, molecular iodine, and molecular sulfur all have oxidation numbers of 0. In monatomic ions, the oxidation number is going to be the same as the charge on that ion. So for example, chloride ions have a -1 charge, and so the oxidation number for a chloride ion is also going to be -1. The oxidation number of the magnesium ion is +2, so the oxidation number is also going to be +2. For sodium, the charge on a sodium ion is +1, so the oxidation number is going to be +1. Now contrast this to rule number 1. In rule number 1, if you had solid sodium that's not an ion, sodium in the solid state, that would have an oxidation number of 0. The sodium ion has an oxidation number of 1. Okay, oxygen has an oxidation number of -2, with the exception of oxygen and peroxides. So for example, in hydrogen peroxide, the oxidation number of oxygen is -1. This is an exception to the rule. Otherwise, it's always going to be -2. So let's look, for example, at an example of how we would assign oxidation numbers. And remember, you have to know the oxidation number because that's going to tell you what's the electron donor and what's the electron acceptor in a particular reaction. So let's look at this compound. It's magnesium oxide. So if we were assigning the oxidation numbers of magnesium and oxygen here, magnesium has a +2, right? Because this right here is an ionic compound. And so if we look at Rule 2, it says in monatomic ions, the oxidation number is the charge of the ion. Magnesium, right, it's 2+, so the oxidation number is going to be +2. And then for oxygen, the oxidation number would be -2. Because oxygen has an oxidation number of -2. Now, these are the same numbers as charges of these things if they were ions, but oxidation state is not the same as the charge on an ion. I just want to make that point. It just oftentimes works out like they're the same number. But you have to use these rules for oxidation state. All right, let's look at there's 2 more rules. Let's look at those. All right, the next rule is about hydrogen. So if it's H plus, or if it's hydrogen on with a nonmetal, it's going to be +1. If it's hydrogen when it's with a metal, it's going to be -1. So let me give you 2 examples. So the first one would be methane. Methane is a nonmetal, right? Carbon is nonmetal, hydrogen is nonmetal. So if we were to figure out the oxidation number of hydrogen in methane, it would be +1, okay? On the other hand, if we had aluminum hydride, we have aluminum and hydrogen. Aluminum is a metal, and so the hydrogen in this compound would be -1. All right, now here's the really important part, is that the algebraic sum of oxidation numbers in a particular compound is overall going to equal 0. So for example, if we have sodium bicarbonate, we have an oxidation number for sodium, we'll have an oxidation number for hydrogen, for carbon, for oxygen. We'll have an oxidation number for each element in this compound, but they'll have to add up overall to 0 because this is a neutral compound. On the other hand, if something is not neutral, the oxidation numbers will sum up to equal the overall charge of that ion. And I'm going to show you how to apply all of these ideas in some practice problems next, and hopefully it'll make more sense. Okay, so let's look at some examples. Let's look at ammonia, for example. And we're going to use those rules to find the oxidation number on nitrogen and hydrogen. So for nitrogen, none of those rules pertain to nitrogen, but we know that there are rules that pertain to hydrogen, so we're going to start with hydrogen. So if hydrogen is bonded to a nonmetal, the oxidation number is going to be +1. The algebraic sum of the oxidation number has to equal 0 for a compound. So we know that if there are 3 hydrogens, each has a +1 charge, that in order to get this to sum to 0, nitrogen is going to have to be -3. And so the oxidation number for nitrogen then is -3, and the oxidation number for hydrogen is +1. So we could use this information in a chemical reaction to determine which one is the electron donor and which one is the electron acceptor. That's why you want to do this. So let's look at another example. Let's look at ClO-. We don't have any rules necessarily for chlorine. In this case, chlorine is not a monoatomic ion, right? It's bonded covalently to oxygen. Right, so this is a non-metal. I mean, it's a polyatomic ion, but it is a non-metal. And so there's not a rule for chlorine, but there's a rule for oxygen. So we can use that information to find out the oxidation number of chlorine. So we know that the oxidation number of oxygen is -2. And we know that the algebraic sum of these oxidation numbers has to equal the overall charge of the ion. The overall charge of this ion is -1. So we could make a little algebraic expression to solve for the oxidation number of chlorine. We could say chlorine is X. Let chlorine be X. X plus -2, that's the oxidation number of oxygen, is equal to -1, which is the overall charge of this ion. So if you solve for X here, you would see that X is +1. So therefore, chlorine has a +1 oxidation number. So chlorine has a +1 oxidation number. Oxygen has a -2 oxidation number. Let's look at one more example. Okay, so for this example, let's look at phosphoric acid. Okay, so we're going to have to find the oxidation number for hydrogen, for phosphorus, and for oxygen. We have rules for hydrogen. Our rules for hydrogen say that when this is bonded to a non-metal, hydrogen has an oxidation number of +1. There we go. For oxygen, we have the rule that says oxygen has an oxidation number of -2. So now we have to use this information to find the oxidation number of phosphorus. I'm going to set this up like an algebraic expression again. I'm going to let X be the oxidation number of phosphorus. So if we have X plus, there's 3 hydrogens. Each hydrogen has an oxidation state of +1. So I'm going to say 3 times +1 plus, there are 4 oxygens. Each oxygen has an oxidation state of -2. So 4 times -2. And the overall charge for this compound, the algebraic sum, has to equal 0. I'm going to let this equal to 0. So I'm going to solve for X. So X plus 3 minus 8 equals 0. So on the left-hand side here we have X minus 5 is equal to 0. So X is going to equal +5. So the oxidation number of phosphorus is +5 then. So we have the oxidation number of hydrogen, we have the oxidation number of phosphorus, and we have the oxidation number of oxygen. And in a redox reaction, you're going to need to find the oxidation number of all of the elements in whatever compound is in the reaction, so that you can find out what the electron acceptor is and what the electron donor is. Alright, so let's look at how you would do that, and how you would recognize that something is a redox type of reaction. So if you have copper
for example, we have the reaction of solid copper and silver ions to form copper ions and solid silver. So if you look here, copper is in a solid state in the reactants. In the product, copper has a 2+ charge, so copper lost electrons. If copper lost electrons, the reaction of copper to copper 2+ is an oxidation reaction. Okay? Let's look at silver. Silver has a +1 charge in the reactants, and in the product, silver has a 0 charge. Silver gained electrons. Therefore, that part of the reaction is the reduction reaction. So we call copper the reducing agent, and we call silver the oxidizing agent. I think that it's the best to figure out what part is the oxidation reaction and what part is the reduction reaction, and remember that if something is in the oxidation reaction, the thing well, the chemical species, copper, is the reducing agent, and then in this case, silver is the oxidizing agent. It's a little confusing since these are opposite words, so you have to figure out how to make that make sense for yourself. But let's look at how you need to apply this for your task. So here we have the combustion of methane. So we need to look and at the reactants here and figure out which one is oxidation and which one is reduction. And let me give you a little mnemonic, and that's Leo goes Gur. So the loss of electrons is oxidation, the gain of electrons is reduction. Alright, so let's deconstruct methane here. So we have carbon and we have hydrogen. So you know that hydrogen has a +1 charge because this is a covalently bonded molecule. So it's two nonmetals together. If hydrogen has a +1 charge, or +1 oxidation number, and there's 4 hydrogens, that means that carbon has to have a -4 oxidation number. So carbon has a -4, hydrogen has a +1. Alright, so let's compare these oxidation numbers here with the carbon in the products. So in the products, we know that oxygen has to have a -2 oxidation number. There's 2 oxygens. We know that this has to overall equal 0, sum to 0. The algebraic sum has to be 0. And so carbon's going to have a +4 oxidation number in the products. So if carbon has a +4 in the products, it has a -4 in the reactants. We know carbon is being oxidized because carbon is losing electrons. So carbon is oxidized. Carbon is oxidized in this reaction. Methane, right, is called the reducing agent. Let's look at oxygen here. So this is molecular oxygen. Remember that I said that anything that is just the element by itself has an overall oxidation number of 0. So
You know that oxygen here has an oxidation number of 0. And then let's look at the oxidation number of oxygen and water. So oxygen has an oxidation number of -2. Hydrogen has an oxidation number of +1. So if oxygen has an oxidation number of -2 on the product side, it has an oxidation number of 0 on the reactant side. Oxygen is reduced. And O2 is the oxidizing agent. I'll write that. We said CH4 is the reducing agent. And O2 is the oxidizing agent. Let's look at one more example. Alright, so we have the nitrate ion reacting with the dichromate ion and H plus to yield chromium 3 plus nitrate. I think I called the reactant nitrate. I meant nitrite. So nitrite plus dichromate plus acid yields chromium 3 plus, nitrate ion, and water. So we want to identify the oxidation, what's being oxidized and what's being reduced in this reaction. So let's look at NO2.
So we know oxygen has to have a -2 oxidation number. We don't know what the oxidation number of nitrogen is, but we can find it out doing a simple algebraic expression. So X for nitrogen for the oxidation state we're solving for, plus there's 2 oxygens. Oxygen has a -2 charge. We know that this has to overall equal -1 because it's the charge of this ion. So we're going to solve for X. So X minus 4 is equal to -1. So X has to equal +3. Alright, so we know the oxidation number of nitrogen.
So let's look over here on the product side and compare. So we're going to do something very similar to what we just did. So oxygen is -2. We have to find out what the oxidation number of nitrogen is. So I'm going to let nitrogen be X again, plus there are 3 oxygens this time. Each oxygen is -2. This overall has to sum to -1. So we have X minus 6 is equal to -1. So X has to equal +5. So now we need to compare these two numbers. So if nitrogen got more positive, it lost electrons. So it lost 2 electrons in this chemical reaction. So if nitrogen lost electrons, remember our mnemonic, Leo goes Ger. Loss of electrons is oxidation. So nitrogen is oxidized in this reaction. So if nitrogen is oxidized in this reaction, I bet that chromium is reduced. So let's show that. I'm gonna shrink all this so that we can do that. All right, so we're gonna look at the dichromate ion. So Cr and oxygen. So we know oxygen's -2. We don't know what chromium is, so we're going to do an algebraic expression. So instead of being X, I'm going to put 2X because there's 2 chromiums. Do you see that there's 2 chromiums in dichromate? So since there's 2 chromiums, I'm going to account for that by making what I solve for 2X. So 2X plus, there are 7 oxygens, each one has a -2 charge, and overall this has to equal -2. Okay, so 2x minus 14 is equal to -2. So 2x is equal to 12. And so that means that x is going to equal +6. So +6. So chromium has a +6 charge, or not charge, but oxidation number in the reactants. And then in the products, well, it's really convenient that we don't have to go through all that algebra again. So chromium in the products has a +3 oxidation number. So we can see that chromium gained electrons because it became less positive. So we know that chromium is reduced. So chromium is reduced, nitrogen is oxidized, all right, and then we also know that NO, the nitrite ion, is the reducing agent. And we know that the dichromate is the oxidizing agent. So here's the thing, the real skill for these kind of problems, right, is recognizing what species is reduced, what species is oxidized.